Let's find out how we can visualize a bitstream as a two-dimensional image. For the purpose of this discussion, I have our random number generator with its two front panel controls. And we need two sub-VIs. One is called Flatten pixmap. Get a little bit of a sense of what this does with the context help window. Seems like there's lots of inputs, but the one that's important here is the one called the 1-bit pixmap, and that generates a data type called image data. The 1-bit pixmap is simply a two-dimensional Boolean array. To display the picture, we use draw flattened pixmap, and that one accepts the results of flattened pixmap, and it can then generate the actual picture as an indicator on your front panel. Now let's turn our attention to getting the one-dimensional Boolean array into a two-dimensional format. So Reshape comes in handy for that purpose. And you could approach this a couple different ways. The way I'm going to do here that seems fairly straightforward is take the length of the bit stream, find its square root, and that finds the best fit square associated with that one-dimensional array. Now the Reshape will need two different input terminals, so that way we're giving square root of length to each, and so we end up with a square image composed of a total number of pixels that matches length. So I wire my one-dimensional bit stream into that Reshape array, and that generates a two-dimensional array. If you look carefully, you can see that the Boolean wire there is a little bit fatter to indicate that it's a two-dimensional array. Since we know what these are, I'm going to remove those labels for now. And easiest here to just create an indicator. And let's see what we got. See what looks to be little flakes of black pepper in the upper left of new picture. Let's make some more bits here. Alright, there we can see a little bit larger patch. Now to try to understand what the mapping is here in terms of what a black pixel means and what a white pixel means, I'm going to create a standard Boolean indicator. And if I make the little LED as small as possible, and then expand the size of the actual indicator itself, this will help us to get a sense of what a true value means in terms of its pixel color. Alright, so it's mostly falses with a couple trues, and if you look at comparing patterns here, we see those two dots correspond to those two true values. You can try another pattern and make the same sort of correspondence. So it looks like true shows up as black. My preference is going to be to look at black as indicating the false value, or what I think of as the binary 0. And use white pixels for true, so we can drop in the NOT gate, if you will, or the inverter, or the complement. Kind of goes by all three of those names, and it looks pretty good. Okay, now as we vary the image size, you'll see that the picture frame always stays the same. That may or may not be a problem for what you're trying to do, but what you find is that if you try to make it smaller to match the size of your image, then as your image grows, the frame doesn't grow, and so sometimes the frame might actually be hiding useful information. So let's learn a technique here that can be used to programmatically control the size of our picture frame. We do this with what's called a property node, and this has got lots of power underneath the hood, so to speak, and what I'm illustrating here is simply the method for getting at the size of that window frame. But if you take a little time to explore that, you'll see there's all sorts of things you can manipulate with property nodes. Now, it's a little bit farther down. Let's try that again. There we go, draw area size. So what's happening here is that this property node knows about the indicator called new picture, and specifically it knows about this property called draw area size. I'm just going to create a constant for now just to get a sense for what kind of information it wants. So this is a cluster of 2 values, probably corresponding to width and height. Well, let's try building our own cluster. What I'll do is bundle together the width and the height that was generated back here from our Reshape array. So we'll bundle those and connect it. All right. Let's run that and see what happens. And actually, let's try making this a bit bigger so we can get larger image sizes possible. Great, so it looks like the frame now automatically adjusts to match the size of the image that you're drawing. Now, I'm a little bit troubled by this coercion dot that's showing up. So let's investigate that just in a little bit more detail. Let me go ahead and try creating that cluster again. Let's see, context help hopefully will tell us the data type inside there. Those say unsigned 32 for width and height. Well, let me see if we can then actually generate an unsigned 32 data type into our cluster here. Looks like the coercion dot is still there. Well, you know, it's working. You could possibly ignore this, but coercion dots sometimes are trying to tell you something that might help you learn something. So let's try another idea here. I'm going to take the cluster constant, wire that into the bundle array. Hey, now it's happy. So there's apparently something about this cluster constant that gives us some additional information that we needed. Now, better yet, I'm going to replace this with the cluster item that's called bundle by name. So now we can explicitly see the width and the height showing up. So now you've got a little better idea about how you might be able to use property nodes in other applications.